Hello all. In this video, we're going to talk about a paradigm-shifting result that is part of one of Einstein's theories that revolutionized the way in which we understand the world around us. This result concerns the passage of time and how the amount of time experienced between two events is not the same for everybody everywhere in the universe. It depends on things. Namely, it depends on how fast you're moving and how strong the gravity is where you are. We're going to focus on the first of these two factors, and by the end of this video, we will have derived a very simple formula that contains within it forward time travel of a sort. And best of all, in order to do this, the most complicated piece of maths we'll need is Pythagoras' theorem. The difficulty in what we're going to do is conceptual rather than mathematical. Before we start, we have to talk a little bit about light and an interesting fact about the speed at which light travels, which will be the cornerstone of all we're going to do today. You may have heard it said that light is an electromagnetic wave, but what exactly does this mean? In the 19th century, the Scottish physicist James Clerk Maxwell had done an enormous amount of work on electric and magnetic fields, discovering that actually these two once thought to be separate phenomena are two sides of the same coin. His equations of electromagnetism, called Maxwell's equations, are a set of equations that link the electric field, the magnetic field, charges, and currents together. Solving Maxwell's equations is not an easy thing, but the simplest solution, where there are no charges and no currents, is quite easy to solve. You might think that this means if there are no charges and currents, that there'll be no electric field and no magnetic field, but actually this doesn't turn out to be the case. If you look at Maxwell's equations in the vacuum case, you find that if you jiggle the electric field, this in turn induces a similar jiggle in the magnetic field, and vice versa, the jiggle in the magnetic field induces a jiggle in the electric field. So if you work through all these calculations, you find that the magnetic and electric fields reproduce one another and actually can carry energy in the form of a wave by producing one another. The electric field jiggling induces a jiggling magnetic field, and the jiggling magnetic field induces a jiggling electric field, and this sort of goes on, carrying energy forwards in a wave. And this is light. This is why we call light an electromagnetic wave. This is also why light can travel in a vacuum without a medium. This electric field producing the magnetic field, producing the electric field, propagating onwards, doesn't need a medium to happen. We would have done all these calculations in a vacuum, without charge and without current, just empty space, nothing but electric fields and magnetic fields. There's another important result about light that comes from these equations, and this is the finite propagation speed of an electromagnetic wave. You can imagine if we have these electric fields jiggling, creating magnetic fields, and so on going on and on, that there is some finite time that it takes for the electric field to stop jiggling and start the magnetic field jiggling, and this to go on and on forwards. And we can calculate this time from Maxwell's equations, and in doing this calculation, we find a constant value for the speed of light. The neat looking equation we get is as follows. C here is the speed of light in the vacuum, and the other two constants, epsilon naught and mu naught, are related to the electric field and the magnetic field in the vacuum respectively. This equation tells us that the speed of light in a vacuum takes a certain constant value that we can calculate from these two experimentally measurable constants, epsilon naught and mu naught. And indeed, when we do experimentally measure these constants and plug in to find what C will be, we do find that it is around 300 million meters per second, which agrees completely with the separate measurements we can take for the speed of light that are independent of the measurements we would take to measure epsilon naught and mu naught. So this backs up our idea that light is an electromagnetic wave. So now we have a new law following from the laws of electromagnetism that tells us that light travels at a certain speed in the vacuum, and this speed is fixed at about 300 million meters per second. And we'll come back to this later. Next, we need to talk about a principle in mechanics, sometimes called Galilean Relativity. To do this, we'll use the example of two people. One sat on a moving train, and the other sat outside of the train, watching it go past. So let's look into this example of the train we talked about. So we have these two men, one on a train, one not on the train. So in this picture, we are looking at the perspective of the man that is not on the train. You can see that he sees the train moving to the right with a speed v, and there is also a bird that he can see that is moving to the left with a speed u. An important thing we have to clarify is that the train is moving at a constant speed. It is not accelerating. Now, for an observer that is moving at a constant speed, like the man with the blue clock on the train, give a special name to this kind of observer. We would call him an inertial observer. So he is not accelerating, and that's an important point because what we're doing at the moment will only be valid for inertial observers. That is, people that are moving at constant speeds with respect to each other. If the train was accelerating, this wouldn't quite work, what we were going to talk about. So now we can take a look at the perspective of the man on the train. So from the point of view of the person on the train, he will see the surroundings moving to the left with a speed v, including the man on the hill moving to the left with a speed v, and he will also still see the bird moving to the left, but now the bird will be moving with a speed greater than u because the velocities have added. And this is basically the crux of Galilean relativity. If you have something moving to the left with a certain speed, and you're moving to the right with a certain speed, the speed of the thing you see moving to the left is its speed plus your speed. The velocities add together like that. Another example, if two men are playing catch, if one man throws a ball to the right with a speed of 3 meters per second, it will hit the other man at the speed of 3 meters per second. But now, if the man on the right is moving to the left, if he's running towards the ball at 2 meters per second, the ball will now hit him at 5 meters per second, which is completely as we would expect. This is not a difficult thing to think about, but it's important to make this point because things will become a little bit less obvious later. Another obvious point is that the time measured on the blue clock will go at the same speed as the time measured on the orange clock. And again, that seems like a funny thing even to specify, because of course they will. But again, later on this will not be the case, so it's important to make this point that in Galilean relativity, clocks move at the same speed. So the blue clock with the man on the train will move at the same speed as the orange clock with the man on the hill. So to summarize, we have the principle of Galilean relativity that says that all the laws of mechanics, for falling balls and rods and normal objects undergoing motion, are the same for all inertial observers. So that is all observers not accelerating, moving at some constant speed. In our discussion of light, we talked about a result predicting a constant value for the speed of light in a vacuum. This is a law of physics. We've also talked about the Galilean principle of relativity. Well, we can extend this, as Einstein did when he published in this area in 1905, to what we will call the Einsteinian principle of relativity. And that is that all laws of physics are the same for all inertial observers, not just the laws of mechanics. This encapsulates the Galilean principle for the laws of mechanics, but extends it, most importantly, to the laws of electromagnetism. We now have an interesting predicament. If Einstein's principle of relativity is correct, all inertial observers will measure the speed of light to have the same value, no matter how fast they're moving, and that seems to not make a lot of sense. If we think back to the example of two men playing catch with a ball, this is like saying that if one man runs at a speed of 2 meters per second towards the incoming ball, and the ball is traveling at 3 meters per second, that he would still catch the ball at 3 meters per second. The speeds wouldn't add, so he wouldn't feel the ball hit him at 5 meters per second, which clearly is not what we experience in real life if you were to go out and do this. But light is special. Nothing can travel faster than light. If we repeated the experiment with torches instead of balls, and the men have some kind of detector on them that can measure how fast light is traveling when it hits them, it wouldn't matter how fast one man would run towards the incoming light beam, the detector on his chest would always measure 300 million meters per second. He could run towards it at 100 million meters per second, and the light comes in at 300 million meters per second. His detector would read the same thing. They wouldn't add to make 400 million meters per second. The speed of light is the same for everyone, no matter how fast you run towards or away from the light source. If we for now take Einstein's principle of relativity to be correct, we can now derive a fantastic result. In order to derive this result, we're going to consider a very special kind of clock known as a light clock. In constructing this clock, we have two reflective plates separated by some distance L, and we imagine a light beam bouncing from the bottom of the clock up to the top, and then back down to the bottom. We define a tick of this clock to be the time taken for the light to go from the bottom to the top and then back down to the bottom. So this clock has some general length L. It doesn't matter. The length of the clock will determine how long the tick is, but we're not too bothered in using this clock as a real clock that will tick once a second. We just want it to measure some finite interval of time. So we will leave the length of the clock to be a general length L. But whatever this length is, if we have a tick length blue delta t, then the length of this clock will be related to the tick length blue delta t by c times blue delta t over 2. And the reason it's over 2 is just because of how we've defined blue delta t, the tick length. We've defined it to be the time to go from the bottom to bottom. So the time taken just to go from bottom to top is half of that, so half of blue delta t. So that is what the length will be, just using distance is speed times time. So this is the clock on the train. So now we want to think about what the person outside of the train will see, the man sat on the hill with the orange clock. So he'll see the train moving to the right with some speed v, and also therefore the light clock moving to the right with some speed v, and he'll still see the light bouncing around inside the clock. But now what he'll see, as the train and the clock are moving to the right, he won't see the light just going vertically up and vertically down. He'll see it following a sort of zigzagged path, as we've shown here. This picture is a what do you call it? Snapshots. This picture shows 3 snapshots of 3 different times as the clock is moving to the right. So here, orange delta t denotes the length of one tick of the blue clock as measured by the man outside of the train, as measured on his orange clock, which ticks in a similar way, but it will turn out not at the same rate. The ticks are not the same. Crucially, after what we talked about the speed of light being constant no matter how fast you run at it, the man outside of the train will still see the light moving in the clock at the speed of light. So he'll see it moving at 300 million meters per second, the same speed that the man on the train will see the light moving at, but he'll see it moving a greater distance in this kind of zigzag. So what we have here is a triangle, a right-angled triangle, where we know all 3 lengths. We know this bottom length here just from taking half a tick length as measured by the orange clock times by the velocity of the train, the velocity the clock is moving to the right at. We know the vertical length, L, as it is just before. This is a physical dimension of the clock we have fixed. And we know the length of the hypotenuse. We know that the light is traveling at a speed c, and we know that the time between the clock being here and the clock being here is orange delta t over 2. So therefore this length of the hypotenuse is c times orange delta t over 2. So we have 3 lengths of a triangle. We know Pythagoras' theorem, so we can put this into Pythagoras' theorem, as we do here. And you can go back in the video and check that I've put the right lengths in the right places. So when we do this, we end up with this equation here, which we can quite easily rearrange for orange delta t. And then if we simplify it, so we divide the numerator and the denominator of this equation by c squared, and then we square root everything, we get this final equation, where I have defined, as is conventional, we define gamma to be this 1 over 1 minus v squared over c squared square rooted. This is called the gamma factor, unsurprisingly. So this result is really quite remarkable. What this tells us is that the time taken for a tick of the blue clock, as measured by someone outside of the train, is not the same as the time taken for a tick as someone would measure inside of the train. So, if the blue clock inside the train ticks with some tick time blue delta t, for the person outside of the train, seeing the train move at a speed v, the speed will instead be this orange delta t, which is the gamma factor times by blue delta t. And this gamma factor is always bigger than 1. So that means that the length of the orange tick, the length of the tick as seen by someone outside of the train, is longer than the length of the tick for the clock inside of the train. So that means that the faster a clock moves, the slower it ticks. The faster you move through space, the slower you move through time, which is really quite a phenomenal result. But we may now stop and say to ourselves, well, surely this can't be true. My watch doesn't go out of time every time I take a train or go for a run. But the important thing to notice is that in our equation, the speed of the traveller comes in as a fraction of the speed of light, and the speed of light is a very big number. For example, for the time you'd experience to change by just 1%, you'd have to be traveling at 42 million meters per second, or 14% of the speed of light, which is enormously faster than anything humans have ever built has ever traveled. If we plot this gamma factor, we can see that it is very close to 1 up to very, very large speeds, so nothing in our everyday experiences is in contradiction with this result. But then what about the speed of light being a constant? Surely this is too weird to be true. If you think that, you wouldn't have been alone 115 years ago, but this postulate is perhaps one of the best tested in all of physics' history. The experiment at the time that first confirmed this was known as the Michelson-Morley experiment, and if you want to read more about that, the Wikipedia article for it is actually very good. So after all this, we're left with the inescapable truth that the way our universe works is far stranger and far more complicated than anyone could have possibly conceived 150 years ago. This isn't some trick or some illusion or some fault in clock design. This is the real change in physical time. If you were to plant seeds of the same kind, some on Earth and some on a rocket, and then that rocket was to fly off at a very high speed for some time, the seeds on Earth would germinate first. If two twins were separated, one staying on Earth and one whizzing off at near light speed in a rocket for some time, when the two twins reunite, the twin on Earth will have aged more. This is real physical passage of time. This is really incredible, and the area of physics that encapsulates this result is known as relativity. Quantum mechanics, together with relativity, completely underpin all modern physics research and have changed the way that we understand the world around us. I hope that if you followed some or all of this video, that in some small way, it has also changed the way that you understand the world around you. Thanks for watching, and if you haven't already, please make sure to follow Cosmic Conundrum on Twitter and take a look at my website link below. Speak to you all soon.